A radio image from the Atacama Desert shows a dying star surrounded by material that should not be colder than the universe around it. The object is the Boomerang Nebula, a faint structure in the constellation Centaurus, and in ordinary visible light, it looks delicate, almost fragile, as if two pale lobes of dust have been pulled away from a central point. In millimeter light, where instruments trace molecules instead of starlight, the picture becomes stranger. Carbon monoxide gas in the nebula absorbs radiation from the cosmic microwave background. That means parts of the outflow are colder than the ancient afterglow left over from the early universe. Cold usually feels simple because on Earth it has familiar signs. Frost forms on glass. Water hardens into ice. Breath becomes visible in winter air. Space removes those familiar signs and leaves only physics. In a near vacuum, there is almost nothing to touch, almost nothing to conduct heat away, and almost nothing that would make cold feel like cold to a human body. Temperature becomes a measurement of motion, radiation, and energy, not a sensation. A place can be flooded with dangerous sunlight and still contain dust grains that radiate away their heat until they are only a few degrees above absolute zero. The coldest places in space are not always the farthest places from stars. Some are hidden inside clouds, where dust blocks light and molecules move slowly enough for radio telescopes to measure their faint rotations. Some are found in the outer solar system, where sunlight arrives as a weak gray illumination after traveling for hours. Some are inside cosmic voids, enormous underdense regions where galaxies become rare and the sky would look almost empty from within. Some are not places in the ordinary sense, but futures, white dwarfs cooling for trillions of years, matter thinning as expansion continues, radiation stretching to longer wavelengths until the universe itself becomes colder than any natural environment now visible. The path into these places begins with a number that appears again and again in cosmology: 2.7 Kelvin. That is not the temperature of a planet, or a nebula, or a dust grain. It is the temperature of the microwave background that fills the observable universe. Every direction in the sky carries this radiation. It is weak now, redshifted by cosmic expansion, but it is still present. It sets a kind of background floor for most of deep space, not because nothing can ever be colder, but because any exposed object will absorb a little of that ancient light. For those drawn to slow journeys through evidence and darkness, subscribing keeps the next one nearby. The subject here is not simply cold as an extreme, it is cold as a record of where energy has gone, how stars die, how gas expands, how matter hides from light, and how the universe changes when there is not enough heat left to make ordinary processes easy. Absolute zero is the point where a system has reached its lowest possible thermal energy. It is 0 Kelvin, or minus 273, 15 degrees Celsius, and no natural object reaches it exactly. The closer a system comes, the less thermal motion remains. At room temperature, molecules in air are racing and colliding constantly. In a molecular cloud at 10 Kelvin, the same basic particles are moving with much less energy. At 1 Kelvin, the motion is slower still, and quantum behavior begins to matter in ways that do not resemble everyday cold. Space itself does not have one temperature. A spacecraft near Earth can have one side heated by the sun and the other side radiating into darkness. A rock in sunlight near Mercury can become extremely hot, while a permanently shadowed crater on an airless world can remain cold for billions of years. A thermometer placed in intergalactic space would not read the temperature of empty nothing. It would interact with the radiation around it, the particles that strike it, and the heat it carries away from its own construction. This is why the phrase coldest place is more complicated in astronomy than it seems at first. Scientists must ask what is being measured. Is it dust temperature, gas temperature, surface temperature, brightness temperature, kinetic temperature, or the effective temperature of an object radiating into space? A nebula can have very cold molecular gas and warmer dust nearby. A dead star can have a surface hotter than a furnace and still be cooling toward a future more frigid than anything now visible. A black hole can have an extremely low theoretical Hawking temperature, while its accretion disk glows with X-rays. The useful question is not only where the coldest place is. The useful question is how the universe makes anything cold at all. On Earth, cold is often produced by contact with a colder reservoir. In space, cold often comes from isolation. Matter loses energy by radiating it away, by expanding, by escaping from dense regions into emptier ones, or by being shielded from starlight. A gas cloud can cool when molecules emit photons. Dust can cool when it radiates in the infrared. Expanding gas can cool because its internal energy is spread through a larger volume. The Boomerang Nebula is the cleanest example of expansion turning into cold. Its central star is in a brief late stage of life, losing its outer layers before becoming a planetary nebula. Material has been thrown outward at high speed. As that gas expands into space, it cools rapidly, much like gas from an aerosol can feel cold when it is released, though the physical scale is entirely different. The result is a cloud whose molecular outflow is measured at around 1 Kelvin, colder than the microwave background that normally warms exposed material from every direction. That one fact makes the Boomerang Nebula feel almost contradictory. It is a dying star, and dying stars are often associated with heat, red giants, glowing shells, ultraviolet radiation, white-hot cores. Yet here the act of stellar death has produced one of the coldest known natural environments. The star is not cold in the simple sense. The system is not quiet or inert. It is losing mass violently by stellar standards, shaping dust and gas into lobes and cavities. The cold exists because energy has been carried outward and diluted faster than background radiation can restore it. At visible wavelengths, the Boomerang Nebula does not reveal its full temperature. The light seen by Hubble is mostly starlight scattered by dust. It shows structure, not cold. The radio and millimeter observations are different. Molecules have rotational transitions, and those transitions leave fingerprints in spectra. When carbon monoxide behaves in a way that can only be explained by gas below the cosmic background temperature, the cold becomes measurable. It is not a mood or a color in the image. It is a consequence of how molecules interact with radiation. The coldest places are often found by looking away from what appears bright. Infrared telescopes look for weak heat from objects too cool to shine visibly. Radio telescopes listen for molecular lines from dark clouds. X-ray telescopes measure the fading heat of compact remnants. Cosmic surveys map where galaxies are missing as carefully as where they cluster. Cold, in astronomy, is frequently an absence that has to be reconstructed from traces. A missing emission line, a faint absorption feature, a darkness in a map that is not empty but underdense. Before reaching intergalactic voids, the nearest cold landscapes are within the solar system. They are not colder than the Boomerang Nebula, and they are not colder than the microwave background, but they show how distance, shadow, and surface chemistry create frozen worlds. On the Moon and Mercury, craters near the poles can have floors that never see direct sunlight. The sun stays low on the horizon there, and crater rims can cast permanent shadows. In those shadows, the surface radiates heat away, but receives very little back. Permanently shadowed regions are cold traps. Water molecules that wander into them can stick to the surface instead of escaping back into space. Over long times, impacts, solar wind chemistry, and cometary delivery may place volatile material in those dark pockets. A map of such a crater is not just a photograph of black terrain. It is a record of geometry. The angle of sunlight, the shape of the rim, the roughness of the regolith, and the slow rhythm of orbital motion determine whether a point on the surface is warmed or preserved. The outer planets and their moons carry cold in a different way. Sunlight at Uranus is almost 400 times weaker than sunlight at Earth. The planet receives so little energy from the Sun that its upper atmosphere can fall to around 49 Kelvin, colder in places than Neptune despite Neptune orbiting farther out. Uranus is strange, not because it is simply distant, but because it appears to release very little internal heat compared with the other giant planets. A world can be cold because it is far from the Sun, but it can be colder still if it has little warmth rising from within. Triton, Neptune's largest moon, has a surface near 38 Kelvin in Voyager measurements, cold enough for nitrogen to behave like a volatile ice. It is not a dead world in the sense of being motionless. Voyager 2 saw dark streaks that suggested geyser-like activity or plumes driven by seasonal heating and volatile movement. That is part of the difficulty with cold worlds. Low temperature does not always mean inactivity. At these temperatures, substances familiar as gases on Earth become landscape materials. Nitrogen, methane, and carbon monoxide can freeze, sublime, migrate, and shape terrains. Pluto widened that lesson when New Horizons flew past in 2015. Before the flyby, Pluto was often imagined as a simple frozen body at the edge of the solar system. The spacecraft found mountains of water ice, plains of nitrogen ice, haze layers in a thin atmosphere, and evidence that volatile ices had moved across the surface. Pluto's surface can be around 33 to 47 Kelvin depending on place and condition, but the cold does not make it geologically meaningless. At Pluto, what is rock-hard water ice can act as bedrock, while nitrogen ice can flow more like a glacier. A cold surface preserves and erases at the same time. It can preserve impact scars because erosion by wind and rain is absent. It can also erase craters when volatile ices flow, sublimate, or settle in layers. The dark red deposits on Pluto, the smooth basin of Sputnik Planitia, and the fractured terrains around it are all signs that cold chemistry has its own geology. It is slower than the familiar processes of Earth and driven by different materials, but it is not simply stillness. Comets carry another kind of cold archive. Far from the Sun, a comet nucleus is a dark, porous mixture of dust, water ice, carbon dioxide, carbon monoxide, and other volatile compounds. Many of those materials formed or were preserved in the cold outer regions of the early solar system. When a comet approaches the Sun, the surface warms, ice turns directly to gas, and dust is carried outward into a coma and tail. The comet becomes visible because stored cold meets new sunlight. Meteorites and returned samples help connect these bodies to laboratory evidence. When scientists analyze material from asteroids or comet-like bodies, they are not touching the temperature of deep space directly. They are studying minerals, organics, isotopes, and grains that formed under cold conditions or survived through them. Some grains in meteorites predate the Sun. They formed around other stars, moved through interstellar space, and became part of the cloud that built the solar system. Cold was part of the preservation chain that allowed those grains to reach a laboratory. Beyond the solar system, cold becomes harder to imagine because there are fewer familiar surfaces. A dark molecular cloud may look empty in visible light, appearing as a black patch against the crowded background of the Milky Way. That darkness is not a hole. It is dust blocking starlight. Inside the cloud, gas and dust can be only about 10 Kelvin. Molecules like carbon monoxide, ammonia, and water ice on grains become tools for measuring conditions that no spacecraft has entered. Molecular clouds are among the coldest large structures in galaxies, and they are also the birthplaces of stars. This is not a contradiction. Cold gas has less thermal pressure, resisting gravity. When parts of a cloud become dense enough, gravity can pull material inward. The collapse is not simple, because magnetic fields, turbulence, rotation, and radiation all interfere. But without cooling, star formation would be much harder. A star begins in darkness, partly because cold allows matter to gather. The instruments that reveal molecular clouds do not see them the way the human eye would. A radio telescope maps emission from molecules. An infrared telescope sees dust glowing faintly or blocking background starlight. A sub-millimeter array traces cold grains and dense cores. The final image may be colorized for interpretation, but the data begin as intensities, wavelengths, and positions. A dark cloud is converted into a map of temperature, column density, velocity, and chemistry. In some regions, starless cores inside molecular clouds become colder than the surrounding cloud. Shielded from starlight and dense enough for dust to block external radiation, their interiors can approach 7 or 8 Kelvin. These are not empty cavities. They are concentrations of gas and dust on the edge of becoming something else. If gravity wins, a protostar may form. If turbulence or magnetic support prevents collapse, the core may remain a cold structure for a time, slowly changing as material drifts and freezes onto grains. The chemistry inside these cores is shaped by cold. At low temperatures, atoms and molecules can stick to dust grains. Carbon monoxide may freeze out of the gas phase. Ices build up layer by layer on microscopic particles. Reactions occur on grain surfaces that would be difficult in open gas. Later, when a young star warms the region, those ices can evaporate and enrich the surrounding gas with more complex molecules. A cold core is not merely a quiet object, it is a chemical reservoir. A telescope image of a stellar nursery often shows glowing colors and bright young stars, but the coldest material is usually not the part that first catches the eye. The bright nebula is gas heated by newborn stars. The cold future is hidden in the dark lanes, where dust blocks the visible light and dense knots wait inside. To understand the place properly, astronomers compare wavelengths. Optical images reveal scattered and emitted light. Infrared images pass through dust more easily. Radio observations trace molecules that survive in the cold. This is one of the central patterns of astronomy. The universe looks different depending on the energy of the light used to examine it. Cold objects are not necessarily invisible, they are visible in different bands. A warm star glows strongly in visible light. A cold dust cloud glows in the far infrared. A molecular transition appears as a radio line. A neutron star can be cold for a neutron star and still visible in X-rays, because its surface temperature is far above ordinary planetary temperatures. The word cold therefore changes meaning from one object to another. A brown dwarf with an atmosphere near room temperature is extremely cold compared with a star. A neutron star with a surface of several 100,000 degrees can be unusually cold compared with other neutron stars of the same age. A void with very few galaxies is cold in the sense that it has little starlight and low matter density, but it still contains the microwave background. Astronomy requires these comparisons because the universe does not use human categories. Brown dwarfs occupy the borderland between stars and planets. They form like stars, from collapsing gas, but they lack enough mass to sustain long-term hydrogen fusion in their cores. Without steady fusion, they cool over time. Young brown dwarfs can be warm enough to glow strongly in infrared. Old brown dwarfs become faint, their atmospheres filling with molecules and clouds. Some are cool enough for water vapor, methane, and ammonia to dominate their spectra. They are not failed in any moral sense. They are objects shaped by mass. WISE 0855 is one of the clearest examples of this cold substellar population. It lies only about 7.2 light-years away, close by astronomical standards, yet it is so faint that it had to be found through infrared motion across images. Its temperature is comparable to cold conditions on Earth rather than to a star. That makes it extraordinary as a brown dwarf, though not extraordinary as a temperature in the universe. It reminds us that there may be many faint objects nearby, not hidden by distance, but by lack of heat. The discovery of objects like WISE 0855 depends on patience with archives. Astronomers compare images taken at different times and look for tiny shifts against more distant background stars. A faint dot moving between frames may be a nearby brown dwarf. It may be a free floating planetary mass object. It may be something difficult to classify cleanly. Motion becomes the clue, because brightness alone is not enough. The coldest nearby neighbors can be almost absent from visible sky maps. Rogue planets push this idea further. A planet ejected from its system, or formed in isolation like a small brown dwarf, may drift through interstellar space without a star. If it has no strong internal heat and no thick atmosphere trapping warmth, its surface can become deeply frozen. If it has a massive hydrogen atmosphere, internal heat may be retained longer. Some speculative models suggest that subsurface oceans might survive under thick ice in special cases, but direct evidence is difficult. These worlds are difficult not because they are far, but because they emit so little light. Direct imaging of free-floating planetary mass objects is easier when they are young and still warm from formation. Old cold rogue planets would be much harder to find. They would not transit a star. They might reveal themselves through microlensing, briefly magnifying a background star as their gravity passes in front of it. Such events are temporary and do not usually allow detailed follow-up. A cold world can announce its presence only through a momentary bending of someone else's light. This is another way cold becomes connected to invisibility. Heat is often what makes an object easy to see. Stars are visible because they radiate. Young planets glow in infrared because they retain formation heat. Accretion disks shine because matter is heated as it falls inward. Remove heat, and the object becomes dependent on reflected light, gravitational influence, or rare alignments. The colder the object, the more astronomy becomes an art of indirect evidence. Cosmic voids are not cold in the same way as a frozen moon or a molecular cloud. They are immense regions where the density of galaxies is far below average. On the largest scales, the universe resembles a web. Galaxies and dark matter gather into clusters, walls, and filaments, while the spaces between them expand into voids. A void may span tens or even hundreds of millions of light years. From inside one, the nearest bright galaxies could be separated by distances that make the sky look sparse. The coldness of a void is mostly a coldness of absence. There are fewer stars to shine, fewer galaxies to heat gas, fewer supernovae enriching the environment, fewer dense clouds collapsing into new systems. But a void is not true nothing. It contains dark matter, thin gas, isolated galaxies, radiation, and the same cosmic microwave background that reaches everywhere we can observe. Even the emptiest known regions are physical parts of the universe, shaped by gravity and expansion. Void formation begins in the early pattern of density fluctuations. Some regions started slightly denser than average, and gravity amplified those differences. Matter flowed toward the denser regions, building filaments and clusters. The underdense regions lost matter relative to their surroundings and became emptier with time. A void is therefore not simply a place where nothing happened. It is a region where large-scale gravity arranged matter elsewhere. Galaxy surveys reveal voids by measuring redshifts. A telescope collects light from many galaxies. Spectra show how much that light has been stretched by cosmic expansion. Those redshifts become distance estimates. With enough galaxies, astronomers can build three-dimensional maps of large-scale structure. Filaments appear as crowded threads. Clusters appear as knots. Voids appear as volumes where the expected points are missing. The emptiness is statistical, built from catalogs rather than from a single photograph. Standing in a cosmic void is not something a human observer can actually do, but the thought experiment helps. The nearest galaxies would be far away. The Milky Way, if placed near the center of a large void, might not have the same neighboring structures in its sky. Navigation by bright nearby galaxies would be poorer. The background microwave radiation would still be there, uniform and cold. Distant galaxies beyond the void would still be visible through powerful telescopes, but the local cosmic environment would feel sparse. Voids matter because they test cosmology. The number, size, and distribution of voids depend on how structure grows. Dark matter affects the gravitational scaffolding. Dark energy affects the expansion rate. Modified gravity theories can predict different void behavior. Because voids are underdense, They are in some ways cleaner laboratories than crowded clusters, where gas physics, mergers, and feedback from black holes complicate the picture. The emptier regions can carry information about the universe as a whole. There is a temptation to describe voids as cosmic darkness, but darkness alone misses the point. A void is a large-scale outcome of structure formation. It has boundaries, internal substructure, faint galaxies, and filaments that can pass through it at lower density. It is not a perfect sphere. It is not a bubble cut out of reality. It is a region in a map where matter has arranged itself unevenly over billions of years. The coldest imaginable point in a void today would still have to contend with the microwave background. A dust grain floating alone in intergalactic space would absorb a small amount of that radiation and radiate in return. Its equilibrium temperature would be close to the background, unless other sources of radiation or particles changed it. The void may be dark, but it is not thermally isolated from the oldest light we can measure. The cosmic microwave background is sometimes treated as a distant relic, but it is local in a practical sense. It passes through the room, through interplanetary space, through galaxy clusters, and through voids. It began when the universe cooled enough for electrons and protons to form neutral hydrogen, allowing light to travel freely. Since then, expansion has stretched that light from visible and infrared wavelengths into microwaves. The universe cooled not by losing the light, but by stretching it. A map of the microwave background shows tiny temperature differences, only about 1 part in 100,000. These variations are not dramatic by human standards, but they are the seeds of cosmic structure. Slightly warmer and cooler regions correspond to early density and velocity patterns in the plasma of the young universe. From those faint differences came the later arrangement of galaxies, clusters, filaments, and voids. The cold afterglow is also a map of where structure would grow. This creates a strange connection. The cosmic microwave background is warmer than the Boomerang Nebula's ultracold gas, but it is also the reason most exposed deep space does not cool below 2.7 Kelvin. It is both a relic and a radiation bath. A cloud can become colder than it only under special conditions, such as rapid expansion and shielding. Once those conditions change, the background begins to matter again. The coldest known natural object is cold, partly because it is temporarily outrunning the thermal floor around it. Temperature in the universe is often a balance between heating and cooling. A dust grain near a star absorbs visible and ultraviolet light and re-emits infrared radiation. A gas cloud can cool by line emission, but it can also be heated by cosmic rays, starlight, shocks, and turbulence. A planet radiates heat into space, but receives energy from its star and perhaps from its interior. A compact remnant cools slowly, while its dense matter retains heat. Cold is not merely the absence of energy, it is the result of competing processes. Dead stars show this competition across extreme timescales. A white dwarf is the exposed core of a low or medium-mass star after the star has shed its outer layers. It no longer produces energy through fusion in the ordinary way. It shines because it is still hot from its earlier life. Over immense periods, it radiates that stored heat away. Young white dwarfs can be very hot. Old ones become cooler, dimmer, and redder. The universe is old enough to contain cool white dwarfs, but not old enough for true black dwarfs. A black dwarf would be a white dwarf that has cooled so much it no longer emits significant light. No confirmed black dwarfs should exist yet, because the time required is longer than the current age of the universe. This makes black dwarfs less an observed population than a future prediction. They belong to a cosmic era that has not arrived. The coldest dead stars, in the ultimate sense, may be objects that the present universe has not had time to make. White dwarf cooling is valuable because it functions as a clock. In star clusters, astronomers can observe the faint end of the white dwarf sequence and estimate ages. The cooler and dimmer the oldest white dwarfs are, the longer the cluster has existed. The method depends on models of cooling, atmospheres, crystallization, and other physics inside dense matter. Even a dead star, fading quietly, becomes a measurement tool for time. Inside a cooling white dwarf, matter is not ordinary rock or gas. The star is supported by electron degeneracy pressure, a quantum mechanical effect that does not require heat in the same way normal pressure does. As the white dwarf cools, carbon and oxygen nuclei can crystallize, releasing latent heat and affecting the cooling rate. This means the path toward darkness is not a simple smooth decline. The interior changes phase. The dead star has an internal history long after fusion has ended. Neutron stars begin at the opposite extreme. They are born in supernova explosions, when massive stellar cores collapse until protons and electrons combine into neutrons, and the remnant becomes one of the densest objects known. New neutron stars are incredibly hot, with temperatures that can begin around billions of degrees internally. They cool rapidly at first by emitting neutrinos, then more slowly by radiating photons from their surfaces. Even an old neutron star can be far hotter than any planet, yet astronomers still speak of cold neutron stars because the comparison is within the neutron star family. X-ray observations can show a neutron star dimmer and cooler than expected for its age. In recent research, some young neutron stars appear tens of times colder than models would predict unless fast cooling processes operate inside them. That makes them important not because they are cold in a human sense, but because their cooling may reveal the behavior of matter at densities no laboratory can reproduce. A neutron star is only about the size of a city, but it can contain more mass than the Sun. Its gravity is so strong that a mountain on its surface would be tiny by Earth standards and still enormous in gravitational energy. Heat does not leave such an object casually. The crust, core, superfluid components, magnetic field, and atmosphere all influence what telescopes measure. When an X-ray spectrum suggests a surface temperature, it is the final visible clue from a chain of physics deep inside the star. The coldest dead stars are therefore not simply the ones with the lowest absolute temperatures today. They are stages in stellar time. A white dwarf cooling toward a black dwarf. A neutron star fading after its birth heat escapes. A brown dwarf cooling because it never sustained hydrogen fusion. A rogue planet losing internal warmth in interstellar darkness. These objects show that cold is the long aftermath of formation. Things are born hot because gravity releases energy. They become cold because space gives that energy somewhere to go. Black holes complicate the idea further. A stellar mass or supermassive black hole surrounded by infalling matter can be part of one of the hottest environments in the universe. Gas in an accretion disk is compressed, sheared, and heated until it shines in ultraviolet and X-rays. Jets can carry energy across thousands of light years. The region around an active black hole is not cold. It is a violent conversion of gravitational energy into radiation. At the event horizon itself, classical general relativity does not assign a normal surface temperature because there is no solid surface. Quantum field theory, however, predicts Hawking radiation with a temperature that decreases as black hole mass increases. For a stellar mass black hole, this temperature is far below the cosmic microwave background. For a supermassive black hole, it is even lower. In that narrow theoretical sense, black holes can be associated with temperatures colder than almost anything else now known. But this does not mean black holes are cold places a spacecraft could visit. The Hawking radiation from astrophysical black holes is overwhelmed by the microwave background and by any nearby matter. They absorb more radiation than they emit. Only in the far future, after the universe has cooled far below today's background, and after galaxies have exhausted their gas, would Hawking radiation become the dominant way a black hole loses energy. The coldest black hole story is mostly a story about the future. The universe is still young compared with its thermal future. Stars are still forming in molecular clouds. Galaxies still merge. White dwarfs are still glowing. Black holes are still fed in many environments. The cosmic microwave background still has a temperature of 2.7 Kelvin. In trillions of years, the background will be redshifted to lower temperatures. New star formation will fade as gas is used up or locked away. The sky will change not suddenly, but through the slow exhaustion of usable energy. When cosmologists talk about the heat death of the universe, they do not mean an explosion or a dramatic ending. They mean a state in which energy differences have been smoothed out so thoroughly that no complex processes can continue in the way they do now. Stars need gradients. Weather needs gradients. Life needs gradients. Computation needs gradients. A universe approaching thermal equilibrium becomes cold not merely in temperature, but in possibility. This future remains model-dependent in its details because it depends on dark energy, particle stability, black hole evaporation, and physics not fully known. Still, the broad direction in the standard picture is clear. Expansion stretches radiation, stars consume fuel, stellar remnants cool, galaxies become darker, black holes dominate for immense spans of time. Then even black holes, according to current theory, evaporate over timescales so long that ordinary numbers lose their intuitive meaning. The coldest places in the present universe are therefore part of a much longer thermal story. The Boomerang Nebula is a temporary cold produced by rapid expansion. Molecular clouds are cold reservoirs that can become stars. Cosmic voids are cold underdense environments shaped by large-scale gravity. White dwarfs and neutron stars are cooling remnants. The microwave background is a universal radiation bath. The far future is the extension of all these processes toward lower energy and fewer active structures. Every one of these environments is known through instruments. The Boomerang Nebula through millimeter observations and scattered light, molecular clouds through radio lines and infrared dust maps, void structure through redshift surveys, white dwarf cooling through photometry and spectra, neutron star cooling through X-ray telescopes, the microwave background through satellite maps that subtract foregrounds, calibrate detectors, and turn tiny fluctuations into cosmological parameters. The coldest places do not announce themselves with brightness. A faint line in a spectrum can matter more than a spectacular image. A map of missing galaxies can matter more than a cluster photograph. A weak infrared point moving across years of data can matter more than a visible star. Cold pushes astronomy towards subtle evidence because cold objects give away less energy. To study them, scientists must measure what little escapes. Consider a molecular line in a radio telescope receiver. The dish collects radiation from a patch of sky that may contain gas spread across light years. Electronics amplify the signal. Software separates frequencies. A spectral line rises slightly above noise. Its width reveals motion. Its intensity suggests abundance and excitation. Its shift gives velocity. A cold cloud becomes a set of numbers. Only later does it become an image with contours and colors. A cosmic void is built in a similar act of translation. There is no single exposure that says void in the way a photograph says moon. Survey teams measure thousands or millions of galaxy redshifts. Algorithms account for selection effects, brightness limits, survey geometry, and foreground contamination. The three-dimensional distribution is reconstructed. Then the empty regions are identified. What appears as nothing is in fact the result of a great deal of measurement. Dead stars require their own translations. A white dwarf's color and luminosity place it on a cooling sequence. A neutron star's X-ray spectrum must be modeled through an atmosphere that may be hydrogen, helium, carbon, or something stranger, under gravity strong enough to alter the escaping light. A brown dwarf's temperature depends on atmosphere models filled with clouds and molecular absorption. The cold is real, but the number comes through interpretation. This does not weaken the science. It is how astronomy works. Almost everything beyond the solar system is known indirectly. No probe has reached a molecular cloud core. No spacecraft has crossed a cosmic void beyond our galaxy. No instrument has landed on a white dwarf. The evidence comes as light, particles, timing, gravity, and comparison with models. The strength of the conclusion depends on how many independent lines of evidence point to the same answer. The coldest known natural object, the Boomerang Nebula, may not keep its title forever. Observational records change. New instruments find fainter objects. A colder expanding outflow could be discovered. A colder starless core may be measured more precisely. A colder artificial environment can be made in laboratories, but that belongs to a different category. In astronomy, record holders are useful because they point toward physical mechanisms, not because the title itself is permanent. The Boomerang Nebula also reminds us that cold is sometimes brief. The star will continue to evolve. Ultraviolet radiation from the central remnant may eventually ionize surrounding material. Dust and gas will expand and interact with the background. The ultra-cold region may warm relative to its current state. A record-setting condition can be a phase, not a destiny. The universe is full of temporary extremes that later become ordinary remnants. Molecular clouds are temporary in another way. A giant molecular cloud may persist for millions or tens of millions of years, but its dense cores collapse, disperse, or are torn apart by newly formed stars. Massive young stars flood their surroundings with radiation and winds. Supernovae can compress some regions and destroy others. The cold that allowed star formation is gradually disturbed by the stars it helped create. A stellar nursery carries its own disruption inside it. Cold dust around young stars has a different destiny. In protoplanetary disks, grains collide, stick, fragment, and sometimes grow into larger bodies. Far from the young star, volatile compounds freeze beyond snowlines. Water ice, carbon dioxide ice, carbon monoxide ice, and other materials appear at different distances depending on temperature and pressure. The architecture of future planets is partly written by where cold allows certain substances to remain solid. The snowline in a disk is not a painted boundary. It moves as the star evolves and the disk changes. Early on, accretion can heat the disk. Later, as material thins, regions cool. Planetesimals form in environments where chemistry, dust size, turbulence, and gravity all matter. The cold outer disk may become the birthplace of comets, icy moons, and the volatile rich material that later affects planetary atmospheres. Cold is part of planet formation, not merely something found after planets are complete. In our own solar system, the distribution of ice carries a memory of temperature. Inside the region where water ice could not survive easily, rocky planets formed. Farther out, ice became abundant and helped build larger cores. Beyond Neptune, small bodies preserved volatile materials in the Kuiper Belt, though billions of years of sunlight, impacts, and radiation have altered their surfaces. The cold outskirts are not untouched, but they hold older chemical information than warmer inner regions. Interstellar objects add a moving clue. When an object from another star system passes through the solar system, its behavior can reveal how much volatile material it carries and how its surface responds to sunlight. A cold body stored for millions or billions of years between stars may awaken briefly near the sun, shedding gas or dust if it still contains accessible ices. The encounter is temporary. The object leaves again, carrying most of its history beyond reach. Cold is also found in the shadows of dense dust around evolved stars. Red giants and asymptotic giant branch stars lose mass through winds, producing envelopes of gas and dust that expand outward. Some of that dust cools as it moves away from the star. Later, when the central star becomes hotter, it can illuminate or ionize the material. Planetary nebulae are therefore not planets, but shells of stellar material shaped by winds, companions, magnetic fields, and time. The Boomerang Nebula belongs to this larger family, but at an unusual moment. It is between phases, not yet a fully developed planetary nebula in the classic glowing sense. Its central system appears to have expelled material rapidly. The cold outflow is part of that transitional violence. A star that once fused hydrogen for millions or billions of years now changes rapidly compared with its earlier life. Human astronomy catches it during a short chapter. Many of the coldest environments are short chapters. A starless core before collapse. A pre-planetary nebula during rapid expansion. A comet far from the Sun before perihelion heating. A white dwarf at a particular point on a cooling curve. Even cosmic voids evolve, though slowly, as expansion and gravity continue to shape their boundaries. Cold is not always the final state. Sometimes it is a stage between one energetic event and another. The instruments used to study cold places are often built to be cold themselves. Infrared detectors must be cooled so their own heat does not drown out the faint heat from the sky. Space telescopes carry sunshields, cryocoolers, or passive radiators. A warm telescope looking for cold dust would see itself. The engineering becomes part of the astronomy. To measure the cold universe, humans first have to quiet the heat of the instrument. The James Webb Space Telescope is an example of this principle. Its mirrors operate behind a large sunshield, separated from the warmth of the Sun and Earth, so the telescope can observe infrared light. It is not the coldest instrument ever built, but its design shows the basic problem clearly. Infrared astronomy is the study of faint heat, and faint heat is easily buried by nearby warmth. The telescope must become part of the cold environment it studies. Ground-based observatories face atmospheric limits. Water vapor in Earth's atmosphere absorbs many infrared and submillimeter wavelengths, which is why high, dry sites matter. The Atacama Desert is valuable not only because the sky is dark, but because the air above it contains little water vapor. ALMA's antennas can study cold dust and molecular gas with precision because the site reduces the interference from Earth's own atmosphere. The cold universe is easier to hear from a dry mountain plateau. Space-based microwave missions face another challenge. To map the cosmic microwave background, they must distinguish the ancient signal from emission by our galaxy foreground dust. Synchrotron radiation, instrument noise, and systematic errors. The final map is not a simple photograph. It is the result of repeated scanning, calibration, subtraction, and statistical analysis. A tiny temperature pattern becomes a foundation for modern cosmology only after every possible foreground has been treated carefully. The scale of cold changes as the story moves outward. A shadowed crater may be tens of kilometers across. A comet nucleus may be a few kilometers wide. A molecular cloud may span dozens or hundreds of light years. A cosmic void may span hundreds of millions of light years. A future cooling universe spans everything. The same word covers many environments because temperature is a physical measurement that can apply across all of them, even when the objects themselves have almost nothing else in common. The most human mistake would be to imagine these cold places as empty because they are not bright. A molecular cloud is full of matter. A void contains structure, just less than average. A frozen moon can have active volatile cycles. A white dwarf is dense enough that a teaspoon of its material would weigh tons on Earth. A cold brown dwarf has an atmosphere with weather and chemistry. Darkness often hides activity at unfamiliar scales. That is why the coldest places in space are not merely settings. They are laboratories. In molecular clouds, cold reveals how stars begin. In protoplanetary disks, cold determines which materials freeze and where planets can form. In brown dwarfs, cold tests atmospheres at the boundary between stars and planets. In white dwarfs, cold measures age. In neutron stars, unusual cooling tests dense matter. In voids, cosmic emptiness tests large-scale structure and expansion. The phrase dead star also needs care. A white dwarf is dead only in the sense that ordinary fusion has ended. It still shines, cools, crystallizes, and influences surrounding objects with gravity. A neutron star is a remnant, but it can spin, pulse, flare, accrete, and generate magnetic activity. A black hole is not a star, but a gravitational remnant in many cases, and it can shape entire galactic centers. Stellar death produces some of the most active and informative objects in astronomy. A cold white dwarf in a telescope image may look unremarkable. It may be a faint point among many faint points. Its importance emerges from color, parallax, spectrum, and luminosity. Gaia measurements can place it in space. Photometry can estimate its temperature. A spectrum can reveal atmospheric composition. Models can connect its brightness to cooling age. The star becomes a clock because observers know how to read the fading ember. In a globular cluster, many white dwarfs can be studied together because the stars share a common distance and age range. The faintest white dwarfs mark the cooling endpoint reached by that population. It is a quiet method, not built on spectacular explosions, but it carries deep time. The dimmest remnants show how long the cluster has been waiting. Cold becomes a calendar written in faint starlight. Neutron star cooling is much less gentle. After a supernova, the remnant loses energy through neutrino emission from its interior. Neutrinos escape easily compared with photons, carrying heat away from dense matter. Later, photon cooling from the surface becomes more important. The rate depends on what particles exist inside, whether superfluidity appears, how the crust conducts heat, and whether exotic states of matter occur. The colder than expected neutron stars are valuable because they narrow the possibilities. A detector on Earth or in orbit does not see the interior of a neutron star directly. It sees X-rays shaped by the surface, atmosphere, gravity, magnetic fields, and interstellar absorption. To infer cooling, researchers compare observed temperatures with ages estimated from supernova remnants or pulsar timing. Every step carries uncertainty, but when several objects appear too cold for their age, the pattern can point toward faster cooling channels in dense matter. This kind of cold is not comforting or picturesque. It is a clue from an environment where atoms are crushed beyond ordinary forms. Neutron stars connect low temperature, in the relative sense, to some of the most extreme physics in the universe. A star can be too cold because something inside it is carrying energy away more efficiently than expected. The mystery is not that the object lacks heat, but that it loses heat in a way models must explain. White dwarfs carry another subtle mystery. Some cooling anomalies have been explored as possible signs of particles beyond the standard model, such as axions, because extra particles could carry energy away and change cooling rates. Most such claims remain constrained rather than confirmed. The point is not that cold stars prove exotic physics. The point is that stellar remnants provide sensitive tests. A small change in cooling over many stars can become evidence for or against new ideas. The coldest places, therefore, have a strange scientific power. Heat can overwhelm details. Cold can expose them. A slowly cooling white dwarf reveals crystallization. A starless core reveals molecular depletion. A cold brown dwarf reveals methane, ammonia, and cloud chemistry. A void reveals structure growth without the confusion of dense environments. A cooled neutron star reveals dense matter physics. Low energy does not mean low information. There is also a deeper historical layer. The universe began in a hot, dense state, and its broad thermal history has been one of expansion and cooling. The first atoms formed when the universe cooled enough for electrons to remain bound to nuclei. The first stars formed when gas cooled and collapsed inside dark matter halos. Later generations of stars enriched space with heavy elements, allowing dust, planets, and complex chemistry. Cooling made structure possible, but structure then created new heat through gravity and fusion. Gravity is the engine that interrupts cooling. As gas collapses, gravitational potential energy becomes heat. Protostars warm. Accretion disks glow. Galaxy clusters contain hot gas because gravity has pulled matter into deep potential wells. Black hole disks shine because falling matter releases enormous energy. Without gravity, the universe would cool more uniformly. With gravity, it becomes uneven, producing bright hot centers and cold dark reservoirs around them. This is why cold and heat are often neighbors. A molecular cloud can contain cold, dense cores near young stars, heating nearby gas. A planetary system can have hot inner worlds and icy outer bodies. A galaxy cluster can contain extremely hot X-ray gas, while its outskirts fade into colder intergalactic space. A dying star can have a warm central source surrounded by an ultra-cold outflow. The universe rarely separates its extremes neatly. The Boomerang Nebula may be colder than the background, but it is also surrounded by a universe full of radiation. The cold gas absorbs microwave photons. Its temperature is measured through that interaction. The very background it defies is part of how scientists know it is so cold. This is one of the elegant parts of the measurement. The ancient light from the early universe becomes a lamp against which a dying star's outflow can be tested. A cosmic void uses the background differently. The microwave background passing through a void can be affected subtly by the integrated Sachs-Wolf effect, where photons gain or lose small amounts of energy as they cross evolving gravitational potentials in an expanding universe. These signals are faint and difficult to isolate. They show that even enormous emptiness can leave a trace in radiation, not by shining, but by slightly altering light that passes through it. In galaxy clusters, the microwave background is changed by hot electrons through the Sunyaev-Zeldovich effect. In voids, the situation is weaker and more subtle. The contrast helps show why voids are not merely empty labels. They participate in the gravitational and thermal history of the universe. Their presence can be studied statistically through correlations between maps, surveys, and models. The coldest darkness becomes part of precision cosmology. A single galaxy inside a void can evolve differently from one in a crowded cluster. It may experience fewer mergers, fewer tidal interactions, and a different supply of gas. Some void galaxies are small, blue, and star-forming. Others show that even underdense regions are not uniform. The void does not prevent galaxy formation entirely. It changes the probabilities, slowing or limiting the processes that build massive systems in denser regions. The nearest large underdense region to us is not a perfect emptiness either. The local void borders our local group environment, influencing flows of galaxies. The Milky Way is not inside the deepest part of a huge void, but our neighborhood is shaped by nearby concentrations and underdensities. Galaxies move not only toward dense attractors, but also away from relative emptiness, in the sense that matter flows out of void regions over cosmic time. Large-scale structure is dynamic. When surveys map this structure, they are looking backward as well as outward. A galaxy's distance means its light left long ago. A map across billions of light years is not a single present-time snapshot. It is a reconstruction through cosmic history, adjusted through models. The farther the survey reaches, the younger the universe appears in that direction. The cosmic web is not only spatial architecture, it is a record of growth over time. Temperature also changes with look-back time. The microwave background was warmer in the past, scaling with redshift. At a redshift of 1, it was about twice today's temperature. In the early universe, it was hot enough to affect gas and chemistry in ways it no longer does. The coldest places available today were not available in the same way then. Cosmic cooling opens new physical possibilities as time passes. This means a future astronomer, if any exist, would inhabit a colder universe, but a poorer observational one. Cosmic expansion will move distant galaxies beyond practical visibility. The microwave background will be stretched to wavelengths harder to detect. Star formation will decline. The sky may contain fewer clues about the early universe. Cold can preserve some things, but cosmic expansion can also remove evidence from reach. The present era is unusually rich for studying cold. The background is still measurable. Galaxies are still visible across cosmic time. Molecular clouds still form stars. White dwarfs have cooled enough to trace ages, but not enough to vanish. Brown dwarfs are faint but detectable with infrared surveys. The universe is cold compared with its beginning, but still active enough to reveal how cold environments work. The word darkness in the title deserves the same caution as cold. Darkness can be a lack of visible light, but it can also be a failure of human eyes. A region dark in optical wavelengths may shine in infrared or radio. A black molecular cloud may be bright in submillimeter emission. A void may look dark because it lacks galaxies, but it still contains radiation. A black hole may be dark at the horizon but surrounded by luminous matter. Darkness is often wavelength dependent. Our eyes evolved for sunlight reflected from surfaces. Astronomy had to move beyond that narrow range. Radio astronomy discovered cold hydrogen and molecular gas. Infrared astronomy uncovered dust-enshrouded star formation and cool objects. X-ray astronomy revealed hot plasma and compact remnants. Microwave astronomy mapped the afterglow of the early universe. Each new wavelength changed what darkness meant. A place in space can be cold because it is shielded from visible and ultraviolet light, but that same shielding can make it luminous at longer wavelengths. Dust grains absorb energetic photons and re-radiate them in infrared. Dense gas emits molecular lines. Cold does not remove the object from physics. It shifts the language in which the object speaks. The problem is building instruments sensitive enough to hear that language. Noise becomes a major character in this story, though it is rarely visible in finished images. A detector has thermal noise. The atmosphere glows. Cosmic rays strike sensors. Electronics drift. Foreground stars confuse faint targets. Survey completeness changes with brightness and color. Cold objects often sit near the detection limit, where a signal must be separated from everything that could mimic it. Many discoveries begin with suspicion rather than certainty. The process of confirming a cold object is often slow. One observation suggests a temperature, another checks the distance. A spectrum tests the composition. A model is revised. A possible contaminating source is ruled out. The object is measured again at a different wavelength. A claim becomes stronger not because the first image looked beautiful, but because the evidence survives attempts to make it ordinary. The coldest places also reveal the limits of language. Calling the Boomerang Nebula the coldest known place in the universe is useful, but known is doing important work. It means measured, recognized, and compared under current definitions. It does not mean no colder natural region exists anywhere. It means no colder natural object has been confirmed in the observable universe with available instruments and agreed methods. Scientific records are statements about evidence. There may be colder regions hidden in circumstances that make them difficult to detect. A rapidly expanding outflow around another dying star might be fainter or more distant. A cold, dense core might be shielded and small. A rogue planet might drift without enough heat to reveal itself. Future surveys may change the list. The correct response is not to weaken the wonder, but to make it more precise. Precision does not make these places less strange. A cloud at 10 Kelvin is still extraordinary. A nebula at 1 Kelvin is still difficult to produce naturally. A void hundreds of millions of light years across is still beyond ordinary intuition. A white dwarf cooling for longer than the present age of the universe before becoming dark is still a profound timescale. Accuracy gives the mystery edges. It lets the mind hold the object without turning it into fantasy. The phrase "dead stars and darkness" points toward the longest arc of all. Stars create light by holding gravity and fusion in balance. When that balance ends, the universe does not simply erase them. It leaves remnants: white dwarfs, neutron stars, black holes, expanding nebulae, enriched gas, and dust. Some remnants remain hot for a long time. Some cool. Some seed future stars and planets. Stellar death redistributes energy and matter across space. The atoms in a dust grain inside a cold molecular cloud may have passed through earlier stars. Carbon, oxygen, silicon, iron, and many other elements were forged or processed in stellar interiors and explosions. Cold clouds are therefore not primordial simplicity. They are built from material with history. A dark cloud may contain the ashes of dead stars, cooled enough to become raw material for new ones. This gives cold a cyclic role. Hot stars create heavy elements. Explosions spread them. Gas cools and condenses. Dust forms and shields new regions. Gravity gathers material. New stars ignite. Planets form in disks where temperature gradients sort chemistry. The cold between stars is not outside the story of light. It is one of the stages that allows light to return in another form. Inside a dark cloud, the density is still extremely low by Earth standards. A laboratory vacuum may contain more particles per cubic centimeter than some interstellar regions. Yet across light years, the mass adds up. Gravity cares about total mass and distribution. A region that feels emptier than any room can still collapse into stars if it is large, cold, and massive enough. Scale changes what emptiness means. Cosmic voids take that lesson further. Their densities are low compared with the cosmic average, but they are enormous. The total amount of matter in a void can still be vast because the volume is vast. The word empty is relative. It means fewer galaxies, lower density, weaker clustering. It does not mean an absence of all particles, fields, or radiation. In cosmology, emptiness has structure. The deepest darkness is sometimes produced by dust rather than distance. The Pipe Nebula, Barnard dark clouds, and other silhouettes in the Milky Way appear as black shapes because they block the dense star fields behind them. Early observers cataloged them as dark markings. Modern astronomy understands them as cold clouds. What looked like a gap in the sky was material, and what looked like absence was the beginning of star formation. A photograph of a dark nebula can be misleading if treated as a window. It is more like a curtain. Behind it, stars continue. Inside it, dust grains carry icy mantles. Gas moves under turbulence and magnetic fields. Dense cores form. The cloud hides visible light because the grains are effective at scattering and absorbing it. In infrared, some of the hidden structure emerges. In radio, the cloud becomes a set of molecular velocities. Temperature measurements in such clouds can come from ammonia lines, carbon monoxide isotopologues, dust continuum emission, and other tracers. Each tracer samples a different part of the environment. Carbon monoxide may freeze out in the densest, coldest regions, making it less reliable there. Ammonia can remain useful at high densities. Dust emission traces grains but requires assumptions about opacity. The measured temperature is always tied to the method. This is why a cold cloud can be debated in detail. Gas and dust may not be at the same temperature in low-density regions. A line of sight may contain layers with different conditions. A telescope beam may average over structures smaller than it can resolve. The coldest point inside a core may be colder than the beam-averaged measurement. Astronomy often sees blended reality, and models separate it carefully. The same is true of distant galaxies. Infrared observations can estimate dust temperatures, but a galaxy contains warm dust near young stars, colder dust in diffuse regions, and perhaps very cold dust hidden in dense clouds. A single temperature can be a simplification. The universe does not present itself as one number. Scientists use simple descriptions when useful, then refine them as data improve. Cold dust in galaxies affects how galaxies look across cosmic time. Dust absorbs ultraviolet and visible light from young stars and re-emits it in the infrared. A galaxy that appears dim in optical light may be actively forming stars behind dust. Far infrared and submillimeter observations have revealed dusty star-forming galaxies in the distant universe that would otherwise be underestimated. Cold material can hide activity until the correct wavelength reveals it. In galaxy clusters, the coldest ordinary matter may sit alongside some of the hottest gas in the universe. Clusters contain plasma at millions of degrees, visible in X-rays. They also contain galaxies with cold molecular gas, dust, and star-forming regions. Some central cluster galaxies show filaments of cooler gas drawn around radio bubbles from supermassive black holes. The contrast is extreme: hot intracluster medium, cold molecular filaments, and relativistic jets in the same environment. This mixture shows why temperature alone cannot define a place. A galaxy cluster is hot overall in its diffuse gas, but cold pockets matter for star formation. A planetary nebula can contain warm ionized gas and colder molecular material. A protoplanetary disk can have a warm surface and a cold midplane. Cold is often layered. The question is where in the system the measurement applies. The cold midplanes of disks around young stars are especially important because they are shielded from direct starlight. Dust settles toward the midplane. Ices form on grains. Chemistry changes as molecules freeze out or are released. Planet formation may begin there, hidden from direct view. ALMA can trace rings, gaps, and dust concentrations in some disks, revealing structures that may be connected to forming planets or other disk processes. The images of disks are often beautiful, nested rings around young stars, dark gaps carved into bright dust emission, asymmetries that suggest pressure traps or gravitational effects. But the beauty is a processed representation of millimeter emission. The cold grains are not shining like lamps. They emit weakly because they have temperature. The image is an instrument's translation of faint heat from material colder than any environment humans can endure without protection. A future comet may begin as dust and ice in such a disk. A future ocean world may gather volatiles because cold preserved them beyond the snow line. A future atmosphere may receive carbon, nitrogen, and water from icy bodies formed far from the young star. Cold determines what remains solid, where it can gather, and how it can later be delivered. Planetary habitability begins partly in regions too cold for liquid water on the surface. The cold places of space are therefore not only remote extremes, they are connected to origins. Stars begin in cold clouds. Planets gather icy material in cold disks. Organic molecules can form or survive on cold grains. Comets preserve some of that material. Dead stars cool into clocks. Voids preserve information about cosmic expansion. Cold marks both beginnings and endings, sometimes in the same physical process. A dying star's outflow can be colder than the early universe's afterglow. A starless core can be cold enough to collapse into a star. A future black dwarf can be a remnant of a star that once warmed planets. These are not separate categories so much as different points in the movement of energy. Heat appears when gravity compresses, when fusion ignites, when matter falls, when shocks pass. Cold returns when expansion, radiation, and isolation take over. Human instruments enter this story as temporary witnesses. A telescope mirror collecting photons from a cold cloud is warm compared with the cloud. A detector must be cooled to avoid seeing itself. A data archive preserves measurements long after the observing night ends. Researchers compare spectra, check calibration, argue over models, and sometimes find that the coldest part of a system is not where the first image suggested it would be. There is restraint in this work because the universe often gives partial answers. The Boomerang Nebula is cold because measurements indicate an ultra-cold outflow, but the full history of the central system involves stellar evolution, possible binary interaction, mass loss, and geometry. Cosmic voids reveal structure growth, but they do not by themselves solve dark energy. Cold neutron stars constrain dense matter, but they do not give a complete equation of state. Each clue is powerful and incomplete. The strongest space mysteries are often like this. They are not blank unknowns. They are known enough to be specific and unknown enough to remain open. The temperature is measured. The mechanism is proposed. The model works partly. The next observation tests what the first could not. Mystery survives because evidence has shape, not because evidence is absent. One of the quietest facts about cold is that it slows many processes but does not stop time. Molecules still rotate and vibrate at quantized levels. Dust grains still collide. Cosmic rays still pass through clouds. Radioactive isotopes still decay inside small bodies. Orbits continue. Gravity continues. A cold moon still moves around its planet. A cold white dwarf still circles the galaxy. A cold void still expands with the universe. In interstellar darkness, cosmic rays can be a subtle source of heat and chemistry. High-energy particles penetrate clouds more deeply than starlight. They ionize molecules, create electrons, and drive reactions even where ultraviolet photons cannot reach. Without cosmic rays, some cold cloud chemistry would proceed differently. A place shielded from light is not shielded from every influence. The galaxy has many ways to disturb stillness. Magnetic fields also matter in cold gas. They can support clouds against collapse, guide charged particles, and shape filaments. Polarized light from dust grains aligned with magnetic fields can reveal field directions. In some regions, gravity pulls material along field lines. In others, turbulence tangles them. A cold molecular cloud is a magnetic, chemical, turbulent environment, not just a dark reservoir waiting passively. Turbulence keeps cold clouds from collapsing all at once. It creates density fluctuations, some of which become cores and some of which disperse. The cloud's temperature sets the sound speed, and the sound speed affects how turbulence behaves. In cold gas, motions that seem modest can become supersonic. Shock waves compress material, changing chemistry and possibly triggering collapse. Cold makes even slow motion dynamically important. This is another way cold shapes the universe. Lower thermal pressure allows gravity to matter on smaller scales. It changes fragmentation, influencing the masses of stars that form. The earliest star formation in the universe depended on how primordial gas cooled through hydrogen molecules and other processes before heavy elements existed. Later, dust and metals made cooling more efficient, allowing different kinds of clouds and stars. The first stars formed in a universe warmer than today's, with different chemistry and no dust from previous generations. They likely were massive compared with many stars now forming, though the details remain uncertain. After they lived and died, they enriched space. Cooling became more efficient in later gas because atoms and dust grains provided new ways to radiate energy. The cold clouds of the modern Milky Way are descendants of a chemically enriched universe. Even the cosmic microwave background affected early star formation. At high redshift, the background temperature was higher, setting a minimum temperature for dust and gas exposed to it. In the far future, the background will be lower, changing the floor again. The coldest possible natural environments are therefore tied to cosmic epoch. A universe at a different age offers different thermal possibilities. A present-day cloud cannot cool below the background unless special circumstances intervene. The Boomerang Nebula shows one such circumstance, but most clouds do not do this. They settle above the background because cosmic rays, starlight, dust emission, and molecular cooling reach a balance. The fact that the boomerang is unusual helps define the ordinary. Most cold places are not record breakers. They are steady compromises between heating and cooling. There is value in the ordinary cold too. A typical molecular cloud at 10 Kelvin is not the coldest object, but it is one of the most important environments in the galaxy. Without cold clouds, the Milky Way would not keep producing new stars. Without cold dust, planetary systems would not assemble in the same way. The record low is fascinating, but the widespread cold does much of the cosmic work. The same can be said for voids. The most dramatic voids attract attention because of their size, but the cosmic web is filled with underdense regions of many scales. Small voids, large voids, walls, sheets, and filaments form a connected pattern. The structure is not a decorative background. It affects galaxy evolution, gravitational lensing, cosmic flows, and how matter moves from the early universe into the present arrangement. Large surveys like the Sloan Digital Sky Survey and newer deep surveys turn the sky into databases. Each galaxy becomes a position, a redshift, a brightness, a color, a spectrum. The cold emptiness between galaxies becomes measurable because the dataset is large enough. One missing galaxy means little. Millions of galaxy positions reveal where matter is not. The coldest darkness often appears only after abundance makes absence statistically clear. From a human point of view, the scale of a void is almost unusable. Light itself may take hundreds of millions of years to cross one. A civilization inside a deep void, if such a civilization existed, might have developed astronomy under a sky with fewer nearby galaxies. The cosmic background would still be available in principle, but the local evidence for large-scale structure would be harder to gather. Environment shapes not only galaxies, but possibly the history of observers. This thought remains speculative, but it points to something real. Observation depends on location. Earth sits inside a galaxy with a rich sky, near other galaxies, in a universe still young enough for distant light to reach us. The cold places we study are accessible because the universe has not yet hidden them completely. We observe from a fortunate thermal and cosmic era after structure has formed, but before the evidence has faded too far. The coldest natural laboratory on Earth is not part of this script's main landscape, but it helps frame the difference. Humans can cool atoms in laboratories to temperatures far below interstellar space, even billionths of a Kelvin above absolute zero. Those are artificial quantum systems, carefully isolated and controlled. The Boomerang Nebula remains special because it is natural and astronomical. The universe did not build a laser cooling apparatus there. It used stellar mass loss and expansion. Laboratory cold and cosmic cold answer different questions. Laboratory ultra-cold atoms reveal quantum behavior in controlled settings. Cosmic cold reveals how large physical systems evolve without walls, pumps, or human control. A molecular cloud cannot be reset for another trial. A white dwarf cannot be adjusted. A void cannot be placed in a chamber. Astronomers work with whatever the universe has already arranged. The connection between cold and time becomes clearer with every example. A comet preserves ancient material because cold slows chemical alteration. A white dwarf cools in a way that records age. The microwave background cools as the universe expands. A molecular cloud becomes cold enough to collapse after previous generations of stars have enriched and disturbed it. Cold is not outside history. It is one of history's measurements. A grain of dust in a cold cloud may spend millions of years coated in ice before becoming part of a disk. It may then join a planetesimal, be heated during impacts, buried inside a larger body, exposed by collision, and eventually fall as a meteorite onto a planet. By the time it reaches a laboratory, its cold history is encoded in isotopes, minerals, and organic residues. The cold itself is gone, but its effects remain. Likewise, a void's history is encoded in the galaxies around it. Their positions, velocities, ages, and star formation rates tell how matter drained away or gathered into walls. A void is not fossilized in rock. It is fossilized in distribution. The map is the archive. Redshift surveys become the equivalent of geological strata, except the layers are built from light travel time and cosmic expansion. Dead stars preserve history in cooling curves. A white dwarf does not remember its life in words, but its mass, atmosphere, composition, and temperature carry information about the star it came from. A neutron star's cooling may carry information about a supernova and the state of dense matter. A black hole's mass and spin may carry a record of mergers and accretion. Remnants are not empty endings. They are compressed archives. When the script title names Dead Stars and Darkness, it reaches toward these archives. Darkness is where faint records wait. A dead star cooling in a star catalog. A dark cloud blocking the Milky Way. A void outlined by missing galaxies. A nebula colder than the background. Each is a different kind of absence, and each absence is measurable because something physical still interacts with light, gravity, or time. The coldest place one could reasonably point to today remains the Boomerang Nebula, but the coldest future place may be everywhere. As cosmic expansion continues, the microwave background will cool further. Exposed objects will equilibrate with a lower radiation bath. White dwarfs will become black dwarfs if matter remains stable long enough. Planets will radiate heat away. Brown dwarfs will dim. The difference between object and background will shrink. In that far future, if black holes dominate, their Hawking temperatures will matter more than they do now. A black hole will be colder than the background until the background falls below its Hawking temperature. Only then will it lose more energy than it gains. For supermassive black holes, that era lies unimaginably far ahead. The present universe is too warm for them to evaporate in any meaningful sense. Even cold black holes are currently warmed by the background they sit in. The final evaporation of black holes, if the theory holds, occurs after timescales that dwarf stellar lifetimes, galactic evolution, and white dwarf cooling. The numbers are so large that they become a kind of mathematical landscape rather than an ordinary duration. Yet the principle is simple. A cold object in a cooling universe can eventually become the warmer one. The direction of energy exchange changes as the background fades. This long view should not make the present feel small in a dismissive way. It makes the present valuable. Right now, the universe contains hot stars, cold clouds, bright galaxies, dark voids, active disks, cooling remnants, and measurable background radiation all at once. Many thermal eras overlap. We can compare them. We can see the afterglow of the beginning while watching stars form from 10 Kelvin clouds and measuring a nebula at 1st Kelvin around a dying star. A single night of observing can connect those scales. One telescope may image a protoplanetary disk. Another may map molecular gas. A space observatory may measure a white dwarf. A survey may add redshifts to a cosmic web map. A microwave mission's archive may refine cosmological parameters. The cold universe is not in one direction. It is scattered through every scale, from shadowed craters to the structure of all visible matter. The question of the coldest place can therefore be answered in layers. The coldest known natural object is the Boomerang Nebula's ultra-cold outflow. The coldest common star-forming environments are dense molecular clouds and starless cores. The coldest planetary surfaces in our solar system include distant icy worlds and permanent shadows. The coldest large-scale environments are cosmic voids, though their temperature is governed by radiation and sparse matter. The coldest dead stars are mostly in the future. Each answer is correct only within its category. This is not a weakness. It is a map. Space is not one environment, but many overlapping physical regimes. Temperature in a gas cloud, on an icy surface, in a compact remnant, and across intergalactic radiation cannot be reduced to a single leaderboard without losing meaning. The careful answer is more interesting because it shows how many ways the universe can be cold. The Boomerang Nebula deserves one more return because it ties many themes together. It is a dying star, a cold outflow, a molecular laboratory, an observational challenge, and a temporary record. Its shape suggests directional mass loss, perhaps influenced by a companion or disk. Its gas expands faster than ordinary winds in many evolved stars. Its temperature reveals how expansion can defeat the background for a while. Its image is beautiful, but its real strangeness is in the spectrum. Imagine the observation not as a postcard, but as a set of measurements. A telescope points. Receivers collect millimeter radiation. The data are calibrated. Lines from carbon monoxide appear. Some regions behave as if they are absorbing the background rather than emitting above it. Models connect that behavior to temperature and motion. A cold outflow emerges from the analysis. The conclusion is not made by staring at blue and red colors, but by reading how molecules treat ancient light. There is an almost circular elegance in that. A star near the end of its life creates gas colder than the light left from the beginning of the universe. The beginning and ending are not philosophically connected in any mystical way. They are physically connected by radiation, expansion, and measurement. The microwave background passes through the nebula. The gas absorbs it. Astronomers detect the effect. A dying star is measured against the oldest light. Molecular clouds connect to the same background more quietly. They usually sit above it, warmed by cosmic rays, nearby stars, and the general radiation field. Their interiors cool through molecular emission until gravity can exploit the low pressure. Stars then form and heat their surroundings. The background remains behind all of this, faint but persistent. It is the baseline against which local astrophysics plays out. Cosmic voids connect to it through scale. A void may contain little light from galaxies, but the microwave background crosses it from all directions. In a simple image, the void is dark. In a cosmological map, it is an underdensity with gravitational influence. In microwave data, its imprint may be subtle. In simulations, its growth helps test the standard model. The emptiness becomes measurable because the universe is filled with fields and radiation. Dead stars connect to the background through future cooling. Today, many remnants are warmer than it. Far in the future, as the background cools, remnants will continue radiating until they approach the surrounding radiation environment. A black dwarf, if it forms, would be a star's old core reduced to a cold remnant. It would be almost invisible except through gravity, occultation, or rare interactions. The sky of that future would hide much of its matter in objects that no longer shine. A cold universe does not mean a simple universe. It may contain degenerate matter, black holes, frozen planets, thin radiation, and particles moving through enormous distances. Complexity would be different, less active, less luminous, and harder to observe. The present cold places are therefore not only destinations, they are previews of physical states that may become more common as the cosmos ages. There is a danger in making that future sound too certain. Proton decay has not been observed. Dark energy may not behave forever as a constant. Black hole evaporation is theoretically strong, but observationally untested for astrophysical black holes. Unknown physics could change the far future. A careful script should allow that uncertainty. The long-term cooling of the universe is a projection from current models, not a witnessed event. What has been witnessed is enough. The cosmic microwave background is measured. Large-scale structure is mapped. Molecular clouds are observed. Brown dwarfs are found in infrared surveys. White dwarfs cool in clusters. Neutron stars are detected in X-rays. The Boomerang Nebula's ultra-cold outflow has been studied with radio and millimeter instruments. These are not guesses. They are pieces of a cold universe already present. A viewer looking at the night sky from Earth sees mostly stars because the human eye selects bright, visible points. The cold universe is hidden between them. It is in the dark lanes, crossing the Milky Way. It is in the infrared glow that eyes cannot see. It is in faint microwave radiation far below visible energy. It is in catalogs of objects too dim for casual observation. It is in the spaces between galaxies where the nearest light may be millions of years away. The sky's apparent stillness also hides motion. Molecular clouds churn, brown dwarfs drift. Comets follow elongated orbits. Galaxies move along filaments. Voids expand relative to their surroundings. White dwarfs cool. Neutron stars spin down. The microwave background stretches. Nothing in the cold universe is truly outside change. The changes are slow, faint, or large scale, which is why instruments and models are needed to see them. A cold place can be dangerous without being dramatic. A human body exposed to vacuum would face pressure loss, radiation, and lack of oxygen before ordinary freezing became the main issue. A spacecraft in shadow must manage heat carefully, not because cold attacks like a substance, but because heat balance determines whether systems survive. Engineers think about radiators, insulation, heaters, and sunlight angles. In space, temperature is designed around as much as endured. The cold places also challenge imagination because they separate temperature from comfort. A neutron star called cold is still lethal beyond comprehension. A black hole with a tiny Hawking temperature may be surrounded by deadly radiation if it is feeding. A molecular cloud at 10 Kelvin is too diffuse to feel like a cold fog. A void is not a room with icy walls. The physical facts are stranger than familiar analogies. That is why the narration should keep returning to measurements. Kelvin, spectral lines. Redshifts, infrared flux, X-ray spectra. Dust emission. Survey maps. These are the handles that let the mind approach environments that cannot be visited. Without them, cold becomes a vague mood. With them, cold becomes a property of matter and radiation. The Kelvin scale itself is one of those handles. It begins at absolute zero, so a temperature of 10 Kelvin is not just minus 263 degrees Celsius, it is 10 degrees above the lower limit. A temperature of 7 Kelvin is less than 3 degrees above that limit. A temperature of 1 Kelvin is astonishingly close. This does not mean all motion stops. It means thermal energy has become extremely low by ordinary standards. At low temperatures, radiation shifts to longer wavelengths. Hot stars peak in visible or ultraviolet light. Cooler objects peak in infrared. Very cold dust emits at far infrared and submillimeter wavelengths. The cosmic background peaks in microwaves. The colder the object, the longer the wavelength of its main emission, and the larger and more specialized the instruments often need to be. Cold stretches light. This is why cold astronomy often looks less like a single sharp photograph and more like layered evidence. A visible image shows stars and scattered light. An infrared image shows warm dust and hidden sources. A millimeter map shows cold grains and molecules. A radio spectrum shows gas velocities. A survey catalog shows where galaxies are absent. The complete object exists only after the layers are compared. In the Boomerang Nebula, visible light shows a shape. Millimeter data reveal the colder outflow. In molecular clouds, visible light shows a silhouette. Radio data reveal gas. In voids, images show galaxies around the edges. Redshift maps reveal the volume. In white dwarfs, a faint point becomes a cooling remnant only when distance, color, and spectrum are known. Cold often requires context before it becomes visible. The coldest places are also places where small amounts of heat matter. A cosmic ray passing through a dense core can change chemistry. A faint interstellar radiation field can warm dust by a few degrees. A companion star can shape a dying star's outflow. A weak internal heat source can keep an icy moon geologically active. At low temperatures, slight energy inputs have outsized consequences because the baseline is so low. This sensitivity is part of why cold systems are valuable. They respond to subtle physics. A white dwarf cooling curve can reveal crystallization. A neutron star temperature can reveal neutrino processes. A protoplanetary disk's ice lines can reveal luminosity history. A void's galaxy population can reveal environmental effects. Cold is not inert. It is responsive in ways that can be measured if the tools are precise enough. The cold universe is also patient. Light from a distant galaxy may cross a void for hundreds of millions of years. A white dwarf may cool for longer than life has existed on Earth. A comet may wait in the outer solar system for millions of years before returning inward. A molecular cloud may drift through the galaxy, forming stars only in some dense pockets. Human observation samples brief moments and processes that do not hurry. That mismatch in timescale is familiar in astronomy, but cold makes it more pronounced. Hot events can announce themselves with explosions, flares, bursts, and shocks. Cold events often require accumulation, long exposures, repeated surveys, archival comparisons, slow cooling, faint emission. The evidence does not arrive as spectacle, it arrives as persistence. A star catalog is therefore part of the cold story. It contains many ordinary points, but among them are white dwarfs, brown dwarfs, subdwarfs, red dwarfs, and faint objects whose motions and colors reveal hidden identities. The coldest objects in the solar neighborhood may not stand out in a casual sky image. They become known when a catalog is cross-matched, when a parallax is measured, when an infrared excess is noticed, when motion refuses to match the background. The coldest known brown dwarfs are close enough that their movement against the sky can be detected across years. This closeness is almost ironic. They are nearby in space and distant in visibility. A bright star thousands of light years away may be easier to see than a cold substellar object a few light years from the sun. Heat, more than distance, determines whether the universe volunteers an object to the eye. In deep fields, the opposite problem appears. Some distant galaxies are bright in infrared because their visible and ultraviolet light has been redshifted by expansion or reprocessed by dust. They are not cold objects in the local sense. They are old light transformed by distance and dust. The infrared sky contains both nearby cool bodies and distant energetic galaxies. Wavelength alone does not tell the story. Context does. This is why astronomers rely on spectra. A spectrum spreads light into its component wavelengths, turning an object from a point into a physical system. Absorption and emission lines reveal atoms, molecules, velocities, temperatures, pressures, and redshifts. For cold objects, spectra can show methane, ammonia, water vapor, carbon monoxide, molecular hydrogen proxies, and dust features. The spectrum is where cold becomes chemistry. Chemistry at low temperature can be slow but distinctive. In cold, dense clouds, deuterium enrichment can become pronounced because reactions favor deuterated molecules under certain conditions. Ices on grains can trap molecules. When warming begins near a protostar, the release of those ices can create rich spectra. The cold phase leaves chemical fingerprints that persist into warmer phases. Star birth begins with a chemical memory of darkness. Some of the molecules detected in space would be destroyed quickly in harsher environments. Shielding allows them to survive. Dust grains block ultraviolet light. Dense gas reduces exposure. The result is an interstellar chemistry that can grow more complex than once expected. This does not mean cold clouds are alive or destined for life. It means chemistry continues under conditions that seem, from Earth, almost impossibly spare. The outer solar system shows a more tangible version of the same principle. Methane on Pluto, nitrogen on Triton, carbon monoxide in comets, and water ice in distant bodies behave according to local temperature and pressure. A small change in sunlight over an orbit can move volatiles from one region to another. Seasonal cycles occur even when the sun is faint. Cold worlds still have weather, though not weather built from liquid water rain. Triton's geyser-like plumes are a useful reminder. At about 38 Kelvin, the word warm loses ordinary meaning, yet sunlight can still drive changes in nitrogen ice. Dark material may absorb slightly more heat. Gas pressure can build beneath translucent ice. Plumes can rise through a thin atmosphere. A world can be cryogenic and active, frozen and changing. Temperature must be understood through the materials present. On Earth, nitrogen is a gas that makes up most of the atmosphere. On Triton and Pluto, nitrogen can be frost, glacier, atmosphere, and migrating volatile. On Earth, water ice is a familiar solid near freezing. On Pluto, water ice is so rigid it can build mountains. The same substances change roles across temperature regimes. Cold rearranges geology by changing what counts as rock, ice, and vapor. This matters for exoplanets as well. A planet far from its star may have water ice as bedrock, methane or nitrogen as surface volatiles, and a thin atmosphere that comes and goes. A planet with internal heat and a thick atmosphere may be warmer than distance alone suggests. A moon around a giant planet may be heated by tides even far from the star. Cold exoplanets cannot be understood by orbit alone. Energy sources must be counted. Direct measurements are difficult. Most exoplanets are found through transits or radial velocity, methods that reveal size, orbit, or mass more readily than surface temperature. Atmospheric spectra can help for some planets, especially large ones or planets around small stars. But cold, distant worlds are challenging. Their signals are faint. Their thermal emission peaks at wavelengths that require sensitive instruments. Many cold exoplanets are known more through inference than direct warmth. Microlensing has found planets at distances from their stars where temperatures may be low and perhaps free-floating candidates. The method is powerful because it does not require the planet to shine. Gravity briefly magnifies a background star. The light curve carries the mass and geometry of the lensing system. But after the event, the planet may not be observable again. A cold world can be detected by gravity and then return to invisibility. This makes cold astronomy feel almost archaeological. The evidence is partial, indirect, and sometimes unrepeatable in the exact same way. A microlensing event occurs once. A comet flyby happens briefly. A supernova remnant cools over decades. A white dwarf sequence preserves long history. A void map reconstructs ancient growth. Astronomers collect fragments and build physical stories that remain open to revision. The coldest places in space ask for that kind of patience. They are not all spectacular in a visual sense. Some are faint, statistical, or theoretical. Their importance lies in what they reveal: how energy leaves systems, how matter organizes when heat is low, how the universe's structure grows, and how future darkness may emerge from present light. A dark frame from a telescope can contain more than it seems. At first, only noise and a few stars are visible. After calibration and stacking, faint sources appear. After spectra are taken, distances emerge. After maps are built, missing regions become voids. After models are compared, the cold background becomes a cosmological measurement. Darkness is often the beginning of analysis, not the end of it. The same is true of a cold spectrum. A weak line may mark carbon monoxide in a molecular cloud. A missing line may suggest freeze out. A broad line may indicate turbulent motion. A line shifted slightly from expectation may reveal gas flowing outward from a dying star. The cold does not speak loudly. It changes the details of light, and the details become the story. In the Boomerang Nebula, the details point to rapid mass loss. In starless cores, details point to collapse or chemical depletion. In brown dwarfs, details point to atmospheric molecules and clouds. In white dwarfs, details point to cooling and composition. In voids, details point to underdensity and cosmic flows. In each case, cold is not a single spectacle but a diagnostic. The most extreme cold known in space is surrounded by ordinary cosmic warmth, and that contrast is part of its meaning. The microwave background is cold by human standards, yet it is warmer than the boomerang's outflow. The outflow is cold because it expanded rapidly. It will not remain the same forever. A record can be transient and still be real. The universe does not preserve extremes for our convenience. The coldest future objects may be nearly impossible to observe from any distance. A black dwarf would emit so little light that only gravity might reveal it. A cold rogue planet would drift silently unless it passed in front of a star or was close enough for faint infrared detection. A cooled universe would contain fewer luminous markers. The more complete the cold becomes, the harder it becomes to know. This is one reason the present evidence matters. The universe still contains contrast. Cold clouds stand against star fields. Cold dust glows against warmer backgrounds. White dwarfs remain bright enough to measure. Voids are outlined by galaxies. The microwave background is still detectable. The present era has not yet lost the gradients that make astronomy possible. A final look at cosmic voids brings the scale back to darkness. In a simulation, matter gathers into a web and leaves broad regions underdense. The image can resemble foam, with galaxies along walls and filaments around empty cells. But the simulation is not decoration. It is a test of gravity, dark matter, expansion, and initial conditions. Observations must match it. Voids are where the model's emptiness must be as accurate as its clusters. The cold inside a void is not like frost. It is low radiation from local sources, low matter density, and a deep reliance on the cosmic background. A lone atom there may travel enormous distances before interacting. A photon may cross without meeting much gas or dust, yet the void still has a history, boundaries, and a role in cosmic dynamics. It is the large-scale version of a lesson repeated throughout astronomy. Empty is rarely absolute. Darkness between galaxies also changes the meaning of distance. In a dense region, galaxies crowd a field of view. In a void, the same field may offer fewer nearby anchors. Light from the far side has traveled longer than the human species has existed by factors beyond comparison. The void is not just a gap in matter, it is a gap across time, a volume where the usual markers of cosmic history are sparse. The human mind often reaches for drama in such places, but the actual science is quieter and stronger. Redshift measurements, galaxy catalogs, density fields, correlation functions, simulations, microwave maps. These are not theatrical tools. They are patient ways of making the invisible, large-scale universe visible enough to discuss. The darkness becomes meaningful because it can be measured. A similar restraint helps with dead stars. A cooling white dwarf is not a ghost. It is a dense remnant following thermodynamics and quantum pressure. A neutron star is not a monster. It is compact matter governed by gravity, nuclear physics, and magnetic fields. A black hole is not simply a hole in space. It is a region where space-time geometry prevents escape from inside the event horizon. Cold does not make these objects supernatural. It makes them physical in another regime. The coldest places in space are sometimes less dramatic than the words used for them. That is not a problem. A real object does not need exaggeration. A 1 Kelvin nebula around a dying star is strange enough. A 10 Kelvin molecular cloud forming stars is strange enough. A cosmic void hundreds of millions of light-years across is strange enough. A future black dwarf older than the current universe is strange enough. The evidence does not require decoration. From the surface of Earth, most of this is hidden behind atmosphere, daylight, weather, and the limits of eyesight. The universe gives humans a narrow biological window, then instruments extend it. A radio dish turns under a dry sky. A spacecraft cools its detectors behind a sun shield. A catalog stores faint sources. A spectrograph spreads light. A supercomputer evolves dark matter and gas through cosmic time. The cold universe becomes knowable through extensions of the senses. Those extensions also have limits. No map includes every galaxy. No model captures every process perfectly. No temperature estimate is free from assumptions. No object is observed from every angle. The honest view of cold space includes uncertainty as part of the landscape. It is not a failure of knowledge, it is the condition under which knowledge is built. If a new survey finds a colder natural nebula, the boomerang will not become uninteresting. It will become one example in a broader class. If a better model changes the inferred temperature of a brown dwarf, the object remains valuable. If neutron star cooling data revise dense matter constraints, the old measurements remain part of the path. Science moves by replacing simple records with deeper categories. The cold traps of the inner solar system deserve more than a brief mention, because they show that darkness can exist close to the sun. Mercury orbits where sunlight is fierce enough to heat exposed rock to hundreds of degrees Celsius, yet radar observations and spacecraft data have shown bright deposits near its poles, consistent with water ice in permanently shadowed craters. The explanation is geometry. Near the poles, the sun never climbs high enough to illuminate some crater floors. Heat is lost to space, and the shadows become cold enough for ice to survive in a place that otherwise seems hostile to anything frozen. The Moon has similar traps. Lunar polar craters contain regions that have not seen direct sunlight for extremely long periods. Instruments aboard lunar orbiters have measured temperatures low enough to preserve volatile compounds, and neutron spectrometers, infrared measurements, and impact experiments have all contributed pieces of the evidence for water and other volatiles. These locations are not cold because the Moon is far from the Sun. They are cold because sunlight cannot reach them easily, and because an airless surface has no atmosphere to carry warmth into the shadow. This makes the polar craters a small-scale version of a larger theme. Cold is often created by isolation from radiation. A crater wall blocks sunlight. Dust blocks starlight. A void lacks nearby galaxies. A detector hides behind a sun shield. A dense core shields its center from the interstellar radiation field. The physical situations are different, but the pattern repeats. Remove the sources of heating, allow heat to radiate away, and a low-temperature environment appears. The Moon's shadows also show how cold can preserve a record of delivery. Water molecules may arrive through impacts, solar wind reactions, or migration across the surface. Once they enter a cold trap, they can remain much longer than they would on sunlit ground. Over time, the shadowed surface becomes a sampling site for processes that operate across the solar system. A dark crater floor can be a storage vault, not because it was designed to preserve anything, but because the energy balance allows molecules to stay. Mercury is even more counterintuitive. The planet has almost no atmosphere, orbits close to the Sun, and experiences intense solar radiation. Yet the polar cold traps survive because there is no air to smear temperature evenly around the globe. The same lack of atmosphere that allows dayside surfaces to become extremely hot also allows shadowed regions to become extremely cold. A world without weather can keep its thermal extremes separated by sharp boundaries. On planets with atmospheres, cold behaves differently. Gas transports heat. Winds move energy from one latitude to another. Clouds reflect sunlight or trap infrared radiation. Seasonal cycles store and release heat. This is why a planet's distance from the Sun is never the whole story. Venus is hotter than Mercury on average because its atmosphere traps heat. Uranus is colder than Neptune in some atmospheric layers because its internal heat flow is unusually weak. Temperature is the result of a system, not a simple address. The outer solar system is filled with surfaces that treat sunlight as a faint influence. On Saturn's moon Iapetus, bright and dark terrains absorb heat differently, helping drive migration of ice. On small Kuiper belt bodies, volatile loss depends on size, distance, reflectivity, and history. Some surfaces become darkened by radiation chemistry over billions of years. The cold does not keep everything pristine. Charged particles, ultraviolet light, micrometeorite impacts, and cosmic rays still alter exposed materials. A frozen surface in space is therefore a living record of competing preservation and damage. Cold slows many reactions, but radiation can still break chemical bonds. Impacts can expose fresh ice or bury old layers. Seasonal warming can move volatiles. Internal heat can fracture crusts. The fact that a world is cold does not mean its surface is unchanged since formation. It means the processes of change are different from those that dominate Earth. Icy moons add another complication. Europa, Enceladus, Ganymede, Titan, Triton, and possibly other worlds may contain internal oceans or subsurface layers affected by heat from tides, radioactivity, or leftover formation energy. Their surfaces can be cold enough to freeze gases or make water ice as hard as rock, while their interiors may remain warm enough for liquid water under pressure. Cold exteriors can hide energy below. A frozen crust is sometimes an insulating lid. Enceladus is especially instructive because its surface is cold, but its south polar region vents material into space. Cassini flew through plumes containing water vapor, ice grains, salts, and organic molecules. The surface temperature alone would not have predicted the full activity. Tidal flexing from Saturn's gravity provides internal energy. The Moon shows that a cold object can be geologically and chemically active when another energy source is available. This matters when thinking about cold exoplanets and rogue worlds. A planet far from its star is not automatically lifeless or geologically inert in every model, but direct claims require caution. Internal heat, tidal forces, atmospheric insulation, and composition can change outcomes. Without measurements, the possibilities remain possibilities. The cold universe invites speculation, but the strongest narration stays close to what can be tested. Some of the most extreme cold in the present universe may occur in small, protected places rather than vast, empty regions. A crater floor can be colder than the average surface of a distant world. A dense core within a cloud can be colder than the diffuse cloud around it. A rapidly expanding outflow can be colder than the cosmic background. The coldest point is often local, shaped by geometry and process rather than by simple distance. The search for cold also depends on how fine the instrument's view is. A telescope beam that covers a large area may average warm and cold regions together. A higher resolution observation can reveal a colder pocket that was hidden in the average. This is true for nebulae, disks, molecular cores, and planetary surfaces. Better instruments do not merely make sharper pictures. They change what counts as the measured environment. In planetary science, thermal infrared instruments can map surface temperature across a body. In radio astronomy, molecular lines can trace gas temperature and density. In submillimeter astronomy, dust emission reveals cold grains, but only through assumptions about how efficiently those grains emit. In X-ray astronomy, a neutron star's spectrum becomes a temperature only after choosing an atmosphere model. Every field has its own translation, from signal to heat. The cold universe is also filtered by selection effects. Surveys find objects they are capable of finding. Infrared surveys discover warm enough brown dwarfs, not necessarily every colder object. Galaxy surveys map voids where galaxies are bright enough to enter the catalog. CME maps reveal fluctuations above the instrument's noise and foreground limits. A record of the coldest known place is always partly a record of what current technology can detect. This is not a flaw hidden at the edge of the science. It is central to the science. Astronomers build completeness corrections, simulate survey limits, and compare independent datasets because they know the sky is not offering a complete list. The unseen cold population may be large. Old rogue planets, faint black dwarfs in the future, small distant icy bodies, and weakly emitting clouds all challenge the census. Darkness is partly physical and partly observational. A place can also be cold in one component and warm in another. In the interstellar medium, dust grains, neutral gas, ionized gas, cosmic rays, and magnetic fields do not always share the same temperature. A region may contain cold atomic hydrogen, warmer ionized gas, and hot supernova-heated plasma nearby. The galaxy is a multi-phase environment. The word cold must be attached to the component being described. Cold neutral hydrogen forms another major reservoir. It is not as cold as the densest molecular cores, but it is crucial for galaxy evolution. The 21-centimeter line of neutral hydrogen allows radio astronomers to map gas across galaxies, including regions far beyond visible stellar disks. Some hydrogen is warm and diffuse. Some is colder and denser. This gas can feed future star formation or reveal interactions between galaxies through tidal streams and warped disks. The 21-centimeter line is one of astronomy's great quiet tools. Neutral hydrogen emits at a wavelength of about 21 centimeters when the spins of the proton and electron in a hydrogen atom flip relative orientation. The transition is rare for any one atom, but in interstellar clouds there are so many atoms that the signal becomes detectable. A radio map of hydrogen is a map of cold and warm gas that visible light would miss. In the early universe, the same line may eventually reveal the cosmic dawn, the time before and during the formation of the first stars. Observing it is extraordinarily difficult because the signal is faint, redshifted to long radio wavelengths, and buried beneath foreground emission from our galaxy and human radio interference. If measured well, it could show how cold hydrogen gas was heated by the first luminous objects. Again, cold becomes a way to study beginnings. The history of the universe includes a period sometimes called the Dark Ages, after the microwave background was released, but before the first stars lit the cosmos. The gas then cooled with expansion, and structure grew under gravity. It was not dark because nothing existed. It was dark because there were not yet stars and galaxies producing abundant light. Neutral hydrogen filled space, matter gathered slowly, and the first luminous sources had not yet ended the darkness. When the first stars formed, they changed the thermal state of their surroundings. Ultraviolet radiation ionized hydrogen. Supernovae heated gas and spread heavy elements. Black holes may have contributed X-rays. The universe moved from a cold, dark phase into a more structured, luminous, and heated one. The cold before the first stars was not an ending. It was a waiting state created by expansion and gravity before fusion became common. The cosmic microwave background preserves the surface from which photons last scattered, but it does not directly show the later dark ages. For that, astronomers look toward redshifted hydrogen and the earliest galaxies. The measurements remain difficult and developing. The cold hydrogen of that era is one of the major frontiers because it connects the smooth early universe to the first structured light. It is another form of cold that is not a place, but an epoch. Epochs can have temperatures just as places do. The early universe cooled from plasma to atoms. The Dark Ages cooled further. The first stars reheated gas locally. Galaxies formed hot and cold phases. The present microwave background sits at 2.7 Kelvin. The future background will be colder. The thermal history of the cosmos is a timeline written in the energy of radiation and matter. On smaller scales, thermal history can be equally important. A white dwarf's temperature tells how long it has been cooling. A planet's internal heat tells how it formed and differentiated. A brown dwarf's spectrum tells its age and mass only through models of cooling. A molecular core's temperature tells whether pressure can resist gravity. The same physical idea appears in many forms. Energy content changes with time, and the change leaves evidence. The difficulty is that temperature can be degenerate with other properties. A faint brown dwarf may be low mass and young, or more massive and old. A white dwarf's luminosity depends on mass, composition, atmosphere, and cooling age. Dust emission depends on temperature and grain properties. A void's apparent emptiness depends on the survey's ability to see faint galaxies. Cold is measured in a web of other variables. This is why long-form astronomy must sometimes slow down. A simple claim is easy to remember, but the careful version is more useful. The Boomerang Nebula is the coldest known natural object because its expanding molecular outflow has been measured near 1st Kelvin. Cosmic voids are not colder than that in a simple thermometer sense, but they are among the darkest and most underdense large-scale environments. White dwarfs will become far colder than today's white dwarfs, but only in the future. A statement like that does more than avoid error. It gives each object its proper scale. It prevents a void from being confused with a gas cloud, a dead star from being confused with a frozen planet, and a theoretical future from being confused with an observation. The universe is already difficult enough without flattening its categories. The coldest places also remind us that science advances through negative space. A void is defined by missing galaxies, a dark cloud by missing background starlight, a cold trap by missing sunlight, a black dwarf by the future absence of light from a remnant. A non-detection in a survey can place an upper limit on temperature or brightness. Absence, when measured properly, becomes evidence. Upper limits are not failures. If a telescope does not detect an object at a certain wavelength, that non-detection can constrain its temperature, size, atmosphere, or distance. Y0855 and similar objects have been studied partly through detections and partly through limits. A faint source not seen in one band but seen in another can reveal extreme color, strong molecular absorption, or very low temperature. The dark part of the data matters. Astronomy therefore has a special relationship with silence. A signal can be meaningful, but so can its absence, provided the instrument was sensitive enough and the expectation was clear. A missing line in a cold core can show freeze-out. A missing galaxy population can define a void. A missing excess heat in white dwarfs can constrain exotic cooling. The cold universe often answers by withholding light in a measurable way. A final category of cold is not a place at all, but a boundary in human knowledge. Absolute zero cannot be reached by finite physical processes. The third law of thermodynamics formalizes the difficulty. Natural systems can approach low temperatures, and laboratories can come extraordinarily close, but 0 Kelvin remains a limit. In cosmic settings, there is also the background radiation, local heating, and the impossibility of perfect isolation. The coldest real places are always above the limit. This gives the subject a built-in humility. No matter how cold the Boomerang Nebula is, it is still not absolute zero. No matter how empty a void is, it is still not nothing. No matter how dark a future black dwarf may be, it still has mass, gravity, and a history. The universe approaches extremes without becoming the simplified version of them. Almost nothing is ever absolute. The same humility applies to darkness. No telescope sees all wavelengths perfectly. No survey sees all objects. No human description captures every component. Darkness may mean low visible light, low matter density, low thermal emission, or low information in a particular dataset. The coldest darkness is not a single condition. It is a family of limits, each one asking for a different instrument. A radio dish under a dry sky, a cryogenic infrared detector behind a sunshield, an X-ray observatory watching a neutron star, and a redshift survey mapping galaxies are all part of the same effort. They extend astronomy into places where ordinary light is weak. They turn cold from a human sensation into a measurable property of dust, gas, stars, planets, radiation, and space-time structure. When these instruments succeed, the result is often quieter than expected. A line on a plot. A temperature estimate with error bars. A catalog entry. A faint contour on a map. A signal just above noise. That is how the cold universe often enters human knowledge. Not as a sudden revelation, but as a small, stable difference that remains after every correction has been applied. The endurance of such small differences is what makes them powerful. The microwave background's tiny fluctuations became the foundation of precision cosmology. The faint cooling of white dwarfs became an age tool. Slight temperature differences in neutron stars became clues to dense matter. Weak molecular lines became maps of star-forming gas. Measured emptiness became the cosmic web. Small signals can carry enormous scale. Cold asks for confidence without overconfidence. The numbers matter, but so do their uncertainties. A 1 Kelvin measurement in an outflow, a 10 Kelvin molecular cloud, a 2.7 Kelvin background, a 49 Kelvin atmosphere, a 38 Kelvin icy surface, a future black dwarf not yet formed. These numbers belong to different systems. They should not be forced into one dramatic sentence. They should be allowed to build a landscape. That landscape stretches from nearby shadows to the far future. It includes places a spacecraft has photographed, clouds mapped by radio dishes, voids reconstructed from galaxy surveys, and remnants understood through models. Some parts are directly imaged. Some are inferred. Some are predicted. Together they show that cold is not a decorative detail of space. It is one of the main ways the universe stores history. History is present even in the darkest frame. The microwave background is a memory of the early plasma. A molecular cloud is the cooled and enriched material of earlier stars. A white dwarf is a stellar core losing heat. A void is the outcome of density fluctuations and gravitational growth. A polar crater's ice may record delivery across billions of years. A cold brown dwarf records formation without sustained fusion. The coldest places are therefore not remote only in distance, they are remote in process. They require the mind to move from sensation to measurement, from image to spectrum, from brightness to absence, from years to billions and trillions of years. They are difficult because they do not resemble ordinary cold, and they are compelling because the evidence is still there. A final measurement problem sits beneath all of this. Temperature is not always directly observed. Astronomers often infer it from how matter distributes energy across wavelengths. A dust grain with a certain temperature emits a predictable spectrum if its properties are known. Gas with a certain temperature excites molecular transitions in certain ways if its density is known. A compact star with a certain surface temperature produces a spectrum shaped by gravity and atmosphere. The number becomes trustworthy when several assumptions are checked against several observations. This is why cold records tend to be revised carefully rather than casually. A better distance changes luminosity. A better opacity model changes dust temperature. A better atmosphere model changes the inferred temperature of a brown dwarf or neutron star. A higher resolution map separates a cold component from a warmer one. Scientific caution can sound slow, but it is the reason a claim about the coldest known object means something at all. The Boomerang Nebula's temperature is remarkable because it survives this kind of scrutiny. It is not simply a blue-looking nebula labeled cold for visual effect. It is a molecular outflow whose behavior against the microwave background requires very low temperature. That distinction matters. In astronomy, color in an image is often chosen to represent wavelength or intensity, while temperature must come from calibrated data. A beautiful image can invite attention, but the spectrum carries the proof. Cosmic voids require a different kind of proof, because the object being measured is an underdensity. A single dark patch on a photograph could be dust, exposure limits, foreground confusion, or simply a field with fewer bright galaxies. A true void appears when distances are measured and the missing galaxies occupy a three-dimensional volume. The cold darkness of a void is not seen all at once. It is assembled from many points that are not where a uniform universe would place them. Dead stars require patience of another sort. A white dwarf cooling sequence becomes meaningful only across populations and time. One white dwarf can be unusual for many reasons. A collection of white dwarfs in a cluster can reveal a pattern. A pattern can test cooling models. The coldest white dwarfs in that group become the edge of a clock. Their dimness is not emptiness. It is the last visible energy of stars that ended their main lives long ago. The far future carries this cooling to an extreme that no telescope can confirm today. If black dwarfs eventually form, they will be stellar fossils in a universe much darker than ours. They may still have mass similar to the Sun, compressed into an Earth-sized body, but without the heat that makes present white dwarfs visible. They would be cold, dense, and almost silent, detectable mainly by gravity or by rare encounters. Their existence is expected only because known physics is allowed to run for far longer than the universe has existed. The same future would change planets. A planet without a star or internal heat would radiate away warmth until it approached the background around it. Atmospheres could freeze, surfaces could become chemically quiet. Orbits might continue around remnants for spans longer than any current biological timescale. The planetary cold of that era would not look like the outer solar system today, because the radiation environment itself would be different. The universe around the planets would have cooled too. This helps explain why present cold places should not be treated as final. They are snapshots in a universe still moving through its thermal history. The Boomerang Nebula will evolve. Molecular clouds will form stars or disperse. Brown dwarfs will cool further. White dwarfs will fade. Voids will continue to expand relative to dense regions. The microwave background will redshift. Each cold place is part of a process, not an isolated monument. A spacecraft crossing the outer solar system provides a useful human-scale image of that process. Its power supply slowly declines. Its instruments are kept within operating temperature by careful engineering. The sun becomes a bright star behind it, rather than a warming presence. Telemetry returns weekly across billions of kilometers. The spacecraft is not measuring the coldest place in the universe, but it is moving through an environment where heat must be budgeted with precision. Mission control rooms translate that environment into voltages, temperatures, pointing angles, and data rates. A thermal reading on a spacecraft is a reminder that cold in space is not an abstract backdrop. It affects metal, fuel lines, electronics, batteries, cameras, and antennas. Human machines survive there only by carrying warmth, controlling radiation loss, and using small amounts of power carefully. The cold universe is encountered first as engineering before it becomes scenery. The observatories studying colder and farther environments face similar discipline. A detector cannot be allowed to glow too much in the infrared. A receiver cannot be allowed to add too much noise. A telescope cannot be allowed to warm unevenly and distort its measurements. The search for cold is also a fight against the heat of the measuring device. To see a faint cold source, the instrument must become quieter than the signal it seeks. There is something fitting about that. The coldest places do not force themselves into view. They require instruments that have been made patient, shielded, cooled, calibrated, and pointed with care. They require observers willing to trust weak signals and also willing to doubt them until the evidence holds. In that sense, cold astronomy has a temperament of its own, restrained, precise, and aware of how easily warmth and noise can hide the truth. When the word darkness appears in this subject, it should carry that restraint. Darkness is not a supernatural boundary. It is where visible photons are few, where matter is sparse, where dust blocks starlight, where radiation has shifted beyond the eye, or where an object has cooled below easy detection. Each darkness has a cause. Each cause can be studied. The universe is not less physical where it is less bright. The same is true of cold. It is not an enemy or a spell. It is a state of matter and radiation created by expansion, distance, shielding, cooling, and time. The closer astronomy looks, the more specific cold becomes. A crater shadow, a volatile ice, a molecular core, a brown dwarf atmosphere, a white dwarf sequence, a neutron star spectrum, a void in a redshift map, a microwave background temperature. The single word opens into many measurements. That is the real shape of the coldest places in space. Not a ranking carved into the universe, but a set of environments where energy has become scarce in different ways. Some are close enough for spacecraft images. Some are distant enough to require radio arrays. Some are so large they appear only in surveys. Some are so far in the future that they exist only as the continuation of physics. Together, they show that darkness is not the absence of a story. It is often where the story has been stored most quietly. A final caution belongs beside every extreme. The coldest known object, the coldest planet, the coldest moon, the coldest cloud, and the coldest remnant are not interchangeable titles. Each belongs to a category, a method, and a moment in observational history. A number without its context can mislead. A number with its context can open a physical world. That is why the most useful answer to the title is not one destination, but a route. It begins with measured cold, moves through shadow and dust, crosses underdense space, follows stars after fusion ends, and continues toward a future that has not yet had time to exist. The coldest places in space are connected by the same question: where did the energy go? The answer changes by scale, but the physics remains traceable through light, motion, and time. The coldest places in space, then, are not only destinations on a list, they are methods of asking what energy does when it is allowed to leave. They show how matter behaves when motion slows, how radiation sets floors, how gravity creates contrast, how expansion changes the background, and how death in stars can produce both heat and cold. They turn darkness into information. Near the end of this journey, return once more to the image from the Atacama data. A dying star, a molecular outflow, a temperature below the afterglow of the early universe. The object is not large compared with a cosmic void. It is not old compared with a white dwarf cooling future. It is not dark in the same way as a molecular cloud. But it gathers the theme into one measurable fact. Under the right conditions, even the universe's background warmth can be undercut. The coldest places are not outside the universe's story. They are woven through it. Cold shadows preserve ice near planets. Cold disks sort the ingredients of worlds. Cold clouds become stars. Cold brown dwarfs fill the gap between planets and suns. Cold remnants measure time. Cold voids reveal the skeleton of large-scale structure. Cold background radiation carries the earliest visible pattern of the cosmos. Nothing in this chain is truly motionless. The shadowed crater turns with its moon. The comet falls inward and outward. The cloud drifts through the galaxy. The void expands. The white dwarf cools. The neutron star loses energy. The background redshifts. Even darkness participates in change, because darkness is not an object, but a condition produced by matter, light, distance, and time. The universe began too hot for atoms, and has cooled enough to make stars, planets, chemistry, and observers possible. It will likely keep cooling on the largest scales, though local gravity will continue to create heat wherever matter can still fall together. The coldest places are therefore not exceptions to cosmic history. They are milestones along it, points where energy has thinned, escaped, or been hidden from ordinary light. A telescope mirror keeps collecting photons long after the first frame seems empty. A radio receiver keeps listening for a molecular line buried in noise. A survey keeps adding galaxies until the missing regions take shape. A cooling remnant keeps fading through a catalog. The cold universe does not rush to explain itself. It leaves traces in weak light, in stretched radiation, in quiet maps, and in the slow movement of matter through darkness.